So last time I gave you this thing to think about, that you have this operator x hat, and these x cats are the eigencats of this operator. And we had proved last time that when it acts on any function f, then the effect of this, the new function, the new cat which you get, its components are just these. So the question was that, so in other words, this is what we proved, that this is just x f of x. So the problem was what are the components, or what are the matrix elements? They are equivalent problems. What are the matrix elements of this operator x hat? In k basis. So in other words, we want to know what are these things, or we want to know that when it acts on a vector, if we know the components of the original one, these are these, then what are the components once I act with this operator x? What is the relation of these guys to these guys? This will tell us, because what we can do, we can always work in the components. This will tell us how does this operator looks in that basis. So based on this, we can say in x basis, x hat is just multiplication by x variable. Because in the x basis, components of f are just f of x, and the action of x changes these components to, under this x operator, it changes to x f of x. While k hat has this form, that if I start with these components, it changes it to these components. Now, the same question we are asking about the k basis. We had already established last time that when you act with k, then in k basis, f is given by these are the components, and under the k operator, these components change into multiplication by k. So this k operator just acts like x operator in the k basis. They are complementary to each other. And we want to now see that how does the x operator looks like in the k basis. So if you have, I can start like this. I project it to k basis to see how does this vector look like in the k basis. And over here, I can insert identity in the position basis, because I want to pick out the action of x hat, which I know how it acts on the position basis. And over here, I can pick out, let me just go on the right-hand side and see how does it look like. So this picks out x because x is an eigenvector of x hat. And this is just f of x. And this is just e to the minus iota kx. Now, I want to get this x. This I know is related to f tilde of x, if this x was not there. Well, I can write this. Let's doing it. F of x. And this gives me exactly this. So now, what does it mean? This part is just f tilde of x, f tilde of k. So what do I have on the right-hand side? I have computed the kth component of the vector when I act with x hat. So it essentially tells me the action of x hat and computing its kth component. So it's telling me that under x hat, f tilde of k goes to iota d by dk f tilde of k. So the effect of x hat in the k basis is this. So it just acts just like the k hat operator in the x basis. It's a derivative. Except for a slight sign change. Over there it was minus, over here it's a plus. And this same thing you can bring over here, write it in this notation. So I have this k x hat f, and over here I have computed this to be equal to f of x. Well, I can even write it. This is what I have found. So on the left-hand side, I can insert, if I want to write it in terms of matrix elements of x, I can insert an identity. Then I have this operator, matrix elements. So essentially, it's called a kernel when you have matrix elements, and this integral is just a sum. So one should think of it as a matrix product. I could have written this k hat like this. So it's literally a matrix product, but in a continuous manner. So how can I get the right-hand side? What should I choose for these guys? Well, it's obvious. I have to choose delta by delta k dash This integral will give me the right-hand side. So these matrix elements are and this delta, when you are given these matrix elements in one basis, this delta is always there because of the continuous nature of the basis. Otherwise, if you just look for the action of this operator, you can remove this delta and just look at this thing. Now, there's an important issue which I want to, by the way, any questions so far? So there's another important issue which we have kind of glossed over. Let us look at this question. Let's ask this question. Is K a Hermitian? It looks like it's Hermitian, at least from its properties, because we have found that it has this basis. It has this set of eigenvectors. So all these K's with K real are eigenvectors of K with real eigenvalues. And they seem to be, this is a basis for our space. So it seems to have the kind of properties which we like about the Hermitian operators, and that's why we deal with the Hermitian operators. And the fact that their eigenvectors form a basis for the space. So we can expand any vector in the eigenbasis of a Hermitian operator. It seems to have that. So looks like it has those properties which a Hermitian operator has. So probably it is Hermitian. However, there is a slight issue. What is the issue? Well, in X basis, we have just seen in X basis, the expression for K is, this is its effect. By the way, when we computed this thing, you can go back and look in the notes that we didn't have to use anything except for the very definition of K hat. What was the definition of K hat? That K hat is the operator. This was almost by definition, which changes these F's to these F tilde naught such that if F of X is equal to this, then this guy is equal to minus iota d by dx f of x. This was the very definition of this operator. And so we didn't have to do anything to get this expression. This is just provided to us. But when we derived this, in that part, we had to do integration by parts. And when we did integration by parts, we assumed that the operators, that the vectors on which it acts must be of this form. We derive this part, that on the k basis it acts this way. If that it acts on only those vectors, so that we neglected this kind of boundary terms. We said that G star and F, they go to 0 at x going to plus or minus infinity. So there was this assumption going in, but we said that we are living in the Hilbert space where we assume this, they are square integrable functions. So this happens for them. We want to be able to integrate them over the whole real line, their modulus square. So if their modulus square is integrable, then these functions better go to 0 at infinity. So we use that part. Now there's a slight issue when we make a statement of this kind. When we say that we have an eigenvector of this operator. So this expression is true. Now with this expression, let me try to find what are the eigenvalues. What are the eigenvectors? So I have is equal to some a f of x. And what are the solutions for this? This is a solution. Gives me. So this is an eigenvector. And since I'm working in the x basis, so this is just a vector k whose components are e to the I kx, which we had just found. But nowhere over here it says that k is real. K is not required to be real in this equation. Even if k is complex, this works. For example, you can check e kappa x, where kappa is real, gives you so this is an eigenvector. But with a complex eigenvalue. So if it has complex eigenvalues, then it can be Hermitian. We don't want these eigenvalues to be there. Well, they are actually, strictly speaking, not there at all. But these eigenvalues are not there because E kappa x is not allowed to be in the Hilbert space. Because if I make any of like if I take the square of it, modulo square, this blows up. So it's not in the Hilbert space. The question is, so if we throw them away, these are not there. That's why complex eigenvalues are not there. But the question is, are these in the Hilbert space? EIKX. Now, if I take two of them, K1x e to the minus I K2x, I'm making something like that. Then this thing, this scalar product is indeterminate because at infinity, this function is going like this. I don't know why my pen is not working properly. So it's an oscillating function. And when you integrate it, you sometimes get plus, you sometimes get minus, and the limit is completely undefined. There's no limit to it. You can't, I mean, you get some thing over here, they keep canceling, but there's no systematic way of deciding that what value would it take at infinity. And that happens at plus infinity and minus infinity. So it's not as bad as this, but it's at least it's not well defined. So strictly speaking, this should not be in the Hilbert space. But if we throw them away, then we do not have any of the eigenvectors of this K operator, which we can use as a basis in for our Hilbert space. So we want to somehow retain them. The same issue, so what we do is we just say that, okay, they have some limit. We by hand, you can say two things, that we by hand take this limit, define this limit so that you get something finite for this integral. Or you can say that we can just include them in our Hilbert space. They're not part of the original L2 space. So we put these extra vectors in to work with. The same issue you can describe, you can address by looking at the definition of hermicity by starting from the very definition of hermicity. So if K is a Hermitian, then this should be equal to what is the definition of hermicity? That this should act on the other side as well. So like this, or to make it more transparent, you can write it like this, flip the order. The effect that K is Hermitian is that you didn't have to replace K by the K dagger over here. So we have to check this. Does this happen or not? This thing, which is by definition, let me write this thing by definition. I can include this identity. There are two identities which I have put in. They give me, this is G star of X. This is F star of x dash, and this was minus iota dx minus x dash d by dx dash. So when I do the integration on dx dash, I get minus iota d by dx f of, there's no star here, f of x. So you can just stick with this. You don't have to write these intermediary steps every time. If you are given this kind of a matrix element, this operator k sandwiched between two operators, you just say that I'm directly working in the x basis. And in the x basis, g looks like g of x. And since it's a bra, so I put in the star. F looks like f of x. And k's expression is minus iota d by dx. And the scalar product, since I'm making a scalar product, is given by integrating over it. That was actually the original scalar product in the L2 space. So that's the definition of this. And I want to check that is it equal to star. So this guy, now I can write that is equal to f star, but then there's a star above it. So it makes it f. And k is minus iota, but there's a star above it. So it's I d by dx. And g is g, but there's a star. So g star. There's the expression. And I want to make it look like this guy. So over here, the derivative is acting on g star. I want to bring it to the f. So all you do is do the integration by parts, and you get minus iota well, let me bring it inside. The derivative shifts to the other guy. Which is exactly same as this, except for this term. So if this term vanishes, then K is Hermitian. So the hermicity of K crucially depends on the domain it acts on. If we take our domain, which was our original Hilbert space, which said that K should act, that F and G go to 0 at x going to plus minus infinity, then this would be fine. Then this would be periodic. Then this term would be 0, and we will be fine. Or if they take periodic values, that f of x times g, f of x and g of x, they go to the same number, they have a limit as x goes to plus or minus infinity. Even then, you will be fine, because this term will not be there. So if I now, but the issue is that I'm also considering these functions. So these will definitely not work. E kappa x, where kappa is real. because they don't go to any finite value at infinity. So this term is just blows up, and you don't have a well-defined limit because you are subtracting some infinity from another infinity, and it's not well defined what is the answer there. But if you have these guys, so when you have one of this and the second, which you're making star, so you have objects like these. And you are looking at how do they look at plus infinity and minus infinity. So again, the issue is that at plus infinity is an oscillatory, and at minus infinity is oscillatory, oscillates between some finite values, between 1 and -1. Doesn't do anything very drastic. But since there's no specific limit, you can't really subtract this from that and get a 0. But you can say that I'm making a prescription that this limit is defined in this way, that they take such value that these guys and these guys cancel. Or you say that what do I want from Hermitian operators? I want them to always have real eigenvalues and their eigenvectors to form a basis. So that those properties are satisfied if I retain these guys in my Hilbert space, even with this property. And then I can make a prescription if I'm checking the hermicity. So how will I check the hermicity? For all other functions which are in the Hilbert space, this will be true because I'll be only considering the functions for which this property is true. Then I say that then there are some other functions which are these, which I will tolerate in my Hilbert space. And I just know that when they act on these, the hermicity has the problem over here, but I just remove it by giving this prescription, or but just by saying, well, what do I want from the function for this operator to be Hermitian? For it to have real eigenvalues and its eigenvectors to form a basis, which does happen if I retain these. So for all practical purposes, it becomes a Hermitian operator, even if I retain these guys. So this is like a little bit of technical thing which you have to do when you are dealing with the eigenvectors of a operator which has continuous eigenvalues. For example, this K. If you treat it, this is somewhat of I would say an easier way to handle with these. Like to address these kind of issues, actually, if you know that the whole theory of whole operator theory was developed because von Neumann wanted to put quantum mechanics on a firm mathematical footing. So he was dealing with these kinds of issues, that when you have these operators, what kind of Hilbert spaces they act on, what are the eigenvectors. So that whole theory develops from there. And if you treat it most carefully, then you live with the fact that this operator doesn't have any eigenvectors, but it still has a spectrum, which you can define in slightly different ways. And then you can't write every vector as a linear combination of the eigenvectors of this operator, but you still have some kind of a dense expression that you can approximate the vectors with some eigenvectors of with some other vectors related to this operator. But we don't need to go there. For most practical purposes, this is good enough, the way we have defined. So any question? Now coming back to the theorem, which I was getting confused. We actually had proved this theorem. So the theorem was any Hermitian operator has a basis any Hermitian operator has a basis of, I shouldn't say has a basis, any Hermitian operator provides us a basis of its eigenvectors. Well, maybe let's write it this way. For any Hermitian operator, we have at least one basis of its eigenvectors, and the operator is diagonal in this basis. So this was the theorem which we proved. Now, we know that, and part of it was, I don't know if we wrote it or not, any two eigenvectors of a Hermitian operator with distinct eigenvalues. I think we wrote it, but let me write it again. With distinct eigenvalues are orthogonal. This proof you can see very quickly that if A is Hermitian and you have this eigenvector and another eigenvector, and W1 is not equal to W2, then what you can do, you can compute this. So AX on this and gives you, but since A is Hermitian, it can act over there. And since eigenvalues, it pulls out a W2, but since eigenvalues of a Hermitian operator are real, so when you pull it out of a bra, it still remains real. So this is equal to this as well. So you have so either this is 0 or this is 0 or both. So if W2 is not equal to W1, then necessarily they are orthogonal. However, if W2 is equal to W1, then you can't say. And that had actually led us to, we had discussed it, like if you have two eigenvectors, two linearly independent eigenvectors with the same eigenvalue, then you have a two-dimensional subspace. How was I writing it? So you have a subspace, you have a eigenvalue W, you have a corresponding subspace, two-dimensional, if you have two linearly independent eigenvectors, then they don't need to be orthogonal. Any linear combination of these two guys is also an eigenvector. So you can pick two non-orthogonal guys over there, and you will still have, they won't be non-orthogonal, they won't be orthogonal. So so they may be distinct eigenvectors, but still having non-zero overlap because the eigenvalues are not distinct. But you can pick up orthogonal vectors as well within this subspace. So this is going to be extremely important, but there is a related theorem which also becomes very important later on. I'm just thinking, should I prove it here or maybe later? Okay, let me just discuss it and quickly try to prove it. Theorem. Two A and B that commute have a common eigenbasis. They have a common eigenbasis, and in which they are both diagonal. So you can choose a basis if A and B commute. Proof. What is, well, I'll just write the proof very colloquially. What does commutation mean? It means on any vector AB is BA. So this people write this way as well. Bring it on this side. And these kind of statements which are true for all vectors, then people just write it as an operator relation. You don't need to write this guy. It's understood that as operators, this is true. And this is given, this notation. The commutator. So the statement is that if this holds, then they both can be simultaneously diagonalized, and they will have a common eigenbasis. There will be a basis which will exist in which they both will be diagonal, and this will be a basis which will consist of eigenvectors which are common to both. So let's continue with the proof. So suppose, let me just first prove the very easier, much easier case. Both A and B are non-degenerate. What does this term mean? Non-degenerate means an operator is non-degenerate if all its eigenvalues are distinct. So they are not repeated. When you solve the characteristic equation, no eigenvalue is repeated. Or in other words, no linearly independent, no two linearly independent vectors have same eigenvalue. So remember, when you have only one eigenvector for a certain eigenvalue, you can still scale it. Multiply it with any number, it remains the eigenvector. So that means you have a one-dimensional subspace corresponding to that eigenvalue. But if that eigenvalue is repeated in your characteristic equation, then that eigenvalue comes up with two different vectors which are linearly independent. You cannot get one from the other by multiplying with a number. So you get a two-dimensional subspace. Similarly, if it's repeated twice, then you will have three linearly independent eigenvectors which all give you the same eigenvalue, and you will have a three-dimensional eigen subspace. If this complication doesn't happen, if all the eigenvalues are distinct, which is many times a case, many times a case, but not all the time, then you have something, then those operators are called non-degenerate. So if A and B are non-degenerate, then you can prove this theorem very easily. So suppose Wi is any eigenvector of A with eigenvalue Wi, then you can do this. BA Wi is equal to Wi, because action of A gives you this number which comes out. But this side, since they commute, I can flip the order. This is equal to AB Wi, which is equal to Wi BWI, because this thing is equal to that. So what is this equation saying? This is saying A acting on this vector gives you the vector back with the same eigenvalue Wi. But since Wi is non-degenerate, Wi is a non-repeated, well, you also call eigenvalues as non-degenerate if they are not one of those. So like an operator can have some single eigenvalues and some repeated eigenvalues. So those which are single, they occur only once, you call them non-degenerate eigenvalues, and the others as degenerate. So since Wi is a non-repeated or a non-degenerate eigenvalue, because I'm assuming that all the eigenvalues are non-degenerate. But since Wi is a non-repeated or non-degenerate eigenvalue, so that means this BWI must be a multiple of Wi. I have only no other vector, this theorem. All other vectors are orthogonal. No other vector is have the same eigenvalue. So you live in the one-dimensional eigenspace. So BWI must be a multiple of Wi of the original eigenvector. It's a one-dimensional eigenspace. But what is this saying? This is saying that Wi is also an eigenvector of B. This is an eigenvalue equation. So whatever are the eigenvectors of A, they will necessarily be also eigenvectors of B. All eigenvectors of A are eigenvectors of B as well. So since I know that there exists a basis of eigenvectors of A, then, and in this basis, and from the previous theorem, in that basis, is like this. Well, because all the eigenvalues are distinct, and the so this is what's happening. When it X over here pulls out WA, and these are orthogonal unless A is equal to B. If the eigenvalues is same. So you have this kind of all the distinct eigenvalues are on the diagonal. This is the previous theorem which we had. But this same basis is common to the B as well. And B will pull out some eigenvalue over here. Let's say, call it nu A. But these guys still remain orthogonal because they are eigenvectors. You don't need to even have that B has distinct eigenvalues. Only one of them, even if one of them has distinct eigenvalues, this will work. Well, did I write? Case on both A and B are non-degenerate. Both doesn't have to be. At least one of them is non-degenerate. Case one, at least one of them is non-degenerate. So whichever is the non-degenerate, you pick its basis. Its basis will be its eigenvectors. They will be orthogonal, and B will automatically have matrix elements which are on the diagonal. Even if these eigenvalues VA are repeated, it doesn't matter. It's a orthogonal basis, and B, since it's an eigenbasis, still an eigenbasis of B, B will automatically be diagonal in this basis. Now, what happens if both are, what if both are degenerate? We know that for one of them, if I pick one of them, say A, then I know that I can still find a basis where this is diagonal. So A will have things like this. Suppose W2 is repeated a couple of times. A, I can always find a basis where A is diagonal. So I start with that basis and see how does B look like. Now I pick an eigenvalue, let's say Wi, which is degenerate, say m times, then what will happen? Then if I repeat this argument, the argument I had, that I pick a vector and act with this, I get where this Wi belongs to this subspace of eigenvalue Wi, which is a m-dimensional subspace. When I flip it, this is equal to so what is this equation is saying? This is saying BWI is also an eigenvector of A hat with same eigenvalue Wi. But cannot say is a multiple of the original starting vector. Because all it tells me, instead, all I have is BWI belongs to this subspace. So what it means is when B acts on any vector of SWIM, it maps it back to a vector of, that's it. Doesn't take you out of there. And that means if I act, so suppose originally in the basis I had chosen, it had these vectors. W1, W2, it had certain degeneracy, so W21, W22, so on. And these by construction I had chosen to be orthogonal because that I can always do for one of them. What I'm now trying to do is find a common orthogonal basis. So you keep going, then you have these guys. One, Wi, I need to correct my settings. Something is terribly wrong with my pen setting. I'll do it in the back. So on up to these m vectors. And it is clear that if I act, so what this statement has said is when I act on any one of them, let's say, I get back to I get a linear combination. Let's say CK. Now, but still, when I make this matrix element, where I is not equal to j, with two distinct eigenvalues, like from two distinct eigen subspaces, this would still be 0. Because I'll get this, but over here, but their scalar product is still they are all 0. Distinct eigenvalues of the operator A, their eigenvectors are orthogonal. So they are 0. So that means when I will construct the matrix of B, matrix of A look diagonal, matrix of B will look like this. For each subspace of A with the degenerate eigenvalues of A will get a block. B will keep these blocks within. All the rest outside will be 0. B will not be diagonal, but B will be block diagonal. Now what you do next is within the space, whatever eigenspace you are considering here, now let's say this block. What is this block? This is in its own right, this is an m-dimensional space. And B is an Hermitian operator in this space. So by our original theorem, in this space, a subspace is a space in all its glory. It's completely a space. It doesn't miss any definition of space. So all theorems apply to subspaces. So within this subspace, B is a Hermitian operator. So by our original theorem, I can find a basis of this subspace which consists of the eigenvectors of B and in which B is diagonal. So discard the previous basis and find the new basis in HWIM where B is diagonal. So any question so far? Now just think for a moment that what happens to the A operator. In this new basis, what will happen to the matrix of the A operator? And I'll give you a minute. I have to take a break for a minute. I'm going to be back. So just think about it, that what happens to the A base, to the A operator? How will its matrix elements look when I make these new linear combinations of the old basis where A was diagonal? What happens to that in this? I'll be back in exactly 1 to 2 minutes. Well, the operator A still remains diagonal because all the elements in this subspace were its eigenvectors to start with. And when I pick a new basis in this subspace, they are still its eigenvectors. And these vectors, new vectors, are by choice still orthogonal. So if I pick elements, these new elements from this basis, two of them, let's say J, these are the new ones now, they have a tilde. They will still give me, and since they are orthogonal, this is same I, only the labeling inside the subspace is different. They are still orthogonal. So they give me still within this basis, this remains diagonal. So I can keep doing it for each block. And what I will end up with is I'll find a basis where both of them are diagonal. And also, I can, yeah, I think I have proved it, but so what you have done is like, before you had some freedom. Within this subspace, you could choose any orthogonal combination. You had, for example, two-dimensional subspace, you can choose any one of them. A will still be log diagonal, but you have a choice. You can pick any one of those. Now, if you bring in B, then you can reduce the choice. So for example, it could be that the B has distinct eigenvalues on these two. If they have distinct eigenvalues on these two, then you can only pick this. This space splits into direct sum of two one-dimensional subspaces, and you cannot rotate between them. Because as soon as you rotate between them, B is no longer diagonal, because you are not picking an eigenvector of B by making a linear combination if these two vectors have different eigenvalues for B. So if you have, this will be used many times, if you have an operator which is degenerate, so it will have a subspace with same eigenvalue, and the subspace has a dimensionality. You want to define it. You want to pick some specific vectors. You cannot label those vectors in the subspace by an eigenvalue. All of them have same eigenvalue. You bring another operator which commutes with A, because you want A to remain diagonal. This new operator B, if it has distinct eigenvalues on this subspace, then you will be choosing more refinement in the subspace, and you will be able to label the eigenvectors. You will be able to label your basis through the common eigenvalue, through the eigenvalues of both of them. And that will pick a more specific basis for you. So let's take 15 minutes break here. We will meet back at exactly 4. And because I really want to try to fix this settings for the pen, it's giving me a lot of trouble. So let's meet at 4. Okay, so let me start and let's get back to with this discussion of this theorem, we can get back to the postulates. So this was the postulate 3, and it says with each, I think postulate 2 we had written that you have with each observable you associate a Hermitian operator. So postulate 3 says when you make an observation of a system for an observable some quantity, the result is one of the eigenvalues of the corresponding Hermitian operator associated with that observable and the probability of getting, when you turn off your mic, the probability of getting a particular eigenvalue W is given by where psi is the state of the system and W is the eigenvector with eigenvalue W of the corresponding operator. So what is it saying? It's the way I have written, I'm just writing it as it comes to my mind, is a bit long, so let's parse it into pieces. So you have a system, and the system, as our first postulate says, will be described by a vector in the Hilbert space. So at any given time, its state will be given by some vector in the Hilbert space. And as we said when we were discussing that postulate, that everything you can know about the system is contained in this vector. Complete description is in this vector. There's nothing more you can do about the system. There's nothing more to know except the information contained in this vector. So depending on the system, there will be a Hilbert Hilbert space associated with that system, which contains its possible states, which are given by the eigenvectors, not eigenvector, the vectors in that Hilbert space. So it will be described, its state will be described by a particular uh, particular vector in the Hilbert space. So it's living in a state psi in the Hilbert space, and you make some observation of some quantity. Observable in common language should be called a quantity or a property, like position, momentum, color, or anything. And when you make this observation, your meters will read something. They will give you an answer. And we are assuming that we have the best possible meters. So within the experimental errors, we're not discussing any experimental errors. The best we can do, the result which will come over the meter reading will be one of the eigenvalues. With each observable, as our second postulate says, we will associate a Hermitian operator. And the postulate says that the result would be one of the eigenvalues of the Hermitian operator. So suppose you want to find the quantity Q, whatever this quantity is, with this would be associated a Hermitian operator. Now we haven't discussed how to associate a Hermitian operator to a quantity. How do we decide uh, which Hermitian operator describes which quantity? There is a prescription. Is a prescription to associate Hermitian operators with quantities or with observables. This is called quantization. But not all of the observable will come through this quantization process. You can have, so this is basically telling you if you have classical mechanical quantities, the quantities which you define usually in classical mechanics like position, momentum, angular momentum, those kinds of things, how to pick Hermitian operators for them. This process is called, this is not quantum mechanics, this is called quantization. We will discuss it in the next postulate, but not all of observable will come through this. There may be other observables which do not come from classical mechanics. So the idea is not even there in the classical mechanics. So in a sense, it's like more like a experimental situation. You want to guess, you want to realize that what kind of observations are possible to describe your system and what are the appropriate Hermitian operators. There's a different approach. There's a slightly, not different approach. There's another point of view you can take that each, well, maybe not each, but pretty much each Hermitian operator on the Hilbert space corresponds to some observable. So you don't quibble at all that which Hermitian operator I should associate with which quantity. You just say that all the Hermitian operators are defining some observations. They are related to some observations. So mathematically speaking, I can start looking at Hermitian operators and they will correspond to some observable quantity. And then it's a different matter. It's a higher order or different problem to figure out that experimentally which quantities they will correspond to. And usually this is like a mix of two. It's a two-way process that you develop theory and at the same time looking at experiments that what kind of things you are trying to observe. But the theory also tells you that what kind of things may be there to observe. So it's a kind of a two-way process between experimental observations and what the theory has to offer to you. But in any case, you can take this relation in either direction, that you have quantities and you have Hermitian operators associated with them, or you have Hermitian operators which will describe for you some observable quantities. So you have this observable quantities, and the postulate says that when you will make an observation, just look for first solve in your theory eigenvalue problem of this operator, and whatever the set you get for the eigenvalues are the only possible things which can turn up in your experimental observation of this quantity. It will be one of these. And which one will be there? Well, if you are in a state psi, psi describes the current state of your system. So with the system, you have the system. With this is associated a Hilbert space. And this Hilbert space has obviously infinitely many elements. And these elements are vectors in this Hilbert space. And these vectors, you pick one that is one possible state of the system. So which state the system is in, well, it's up to system or it's up to how you have prepared. But the postulate is saying that when it is in a particular state, well, it will always be in one particular state because that has its complete description. When it's in one of these states, how to then predict that when you make an observation, what value will come out? So you are in this state psi. Which one of these? So let me write them like a list like this, could be infinite. Which one of this will turn up? Well, it says that there's only a probability. You cannot predict with certainty. Many of them can turn up. And there's only a probabilistic answer. Answer. So the probabilities are inherent. It's not because of any lack of information. It's just how the theory is set up. When you can know the best about the system, the complete information is in the state psi. Still, you cannot answer that if you make an observation, which of the answers will come out. But it tells you what would be the probability. And the probability would be proportional to making this scalar product of psi with the corresponding eigenvector and taking the mod square. Now, I have only written that it's a proportionality. Well, you can write it in the following form as well. The same thing, because of the theorem that the eigenvectors of a Hermitian operator provide me a basis for my space, I can expand this psi as a linear combination of the eigenvectors of this Hermitian operator whose probabilities I am looking at. So then what is this? From this linear combination, this is just equal to and since they are, for now, I'm assuming that they're not degenerate, then this will pick for me aj mod square, because this gives me delta ij. So that means if I write psi as a sum linear combination of eigenvectors, which I have normalized. I'm assuming that I'm writing the eigenvectors in the normalized form so that their norm is 1. You can always do it. No loss of generalization in doing that. Then the probability of any one of them, let's say p omega 3, is just you pick the coefficient in this linear combination. Well, it's proportional. You pick the coefficient in this linear combination and make the mod square. Now, we have that if I want to make it an equality, then what do I have? So this is, if I put it equal to AI mod square. With equality, I have this condition. Should be equal to 1 because the probabilities must sum to 1. So this implies AI mod square is equal to 1. So what would that mean? That would mean that if I write it like this, and if I compute this norm, This is delta ji. So this gives me one of them breaks down. And I get ai mod square. But this is equal to 1. If I want them equal to be probabilities and probabilities summing to 1, this implies I should take psi equal to 1. So if I have this condition, I don't need to take this condition, but if psi is equal to 1, then this proportionality becomes an equality. This kind of condition, this you could say that the state vector, so the vector which you associate to describe the state of the system is also called the state vector. Psi is normalized. You don't really need to normalize. Even if you don't normalize, you can work with it as long as you know that you are talking about relative probabilities. So if this is like this, and you haven't normalized the psi is not normalized, you can put an equality by dividing by this. Because what do you have? You have, if I sum them now, this comes out outside. This mod square, you can write it like this. Psi star omega I psi. But I can flip it. And this is just identity because I'm summing over all possible values. So this becomes 1. So that means if I write this, even then it is proper probability that sums to 1. And is consistent with our previous assertion, because if this is 1, if this is normalized, then this goes to this formula. If it's not normalized, we were saying that probabilities, I can pick up these coefficients which come in the expansions. This is exactly equal to, so these coefficients is proportional to these coefficients. So you know that if you want to normalize a probability, you can take the sum of all of them and divide by this sum. So let's say this is pseudo probability. This is relative probability. So you define new one by dividing by this sum. That will automatically be a normalized probability. Because when you will add different one of them, you will get in the numerator same thing as the denominator, and that would be 1. But what are these things? What is this thing? This, I'm just doing it because to give you practice that all of these things are very closely related. What is this guy? Each one of them is mega 1 mod square. So this is expression is actually equal to summation I mega 1 psi mod square mega I. But that's exactly this. Which we found is equal to psi by psi. And this is equal to so if you use this formula, you don't need to normalize psi, but you can normalize psi. So all we care about is all the information in psi, information is brought out through these probabilities. That's all you have. And so that means if I change psi, if I change it by multiplying with any complex number, a psi, what happens to the probability? Goes to a star, a psi mod square over psi. Well, just no a comes from here because I'm just scaling psi. So from up, a mod square comes out because there's a mod square here. And from down, when I bring this out, I get a mod square. So none of the predictions of the theory change if I scale by a number. That means the system, the state, does not correspond to one specific vector in Hilbert space, but rather a whole line. People call it a whole way. So you take psi, multiply it with any number, doesn't have any effect on the predictions of the theory. But it's convenient to choose psi because I can choose any psi from this way. Convenient to choose psi so that psi by psi is equal to 1. For one thing, I wouldn't have to write this again and again. I wouldn't have to compute this and divide by this. So once normalize psi for once, and then you can just use a slightly simplified formula. So convenient to choose psi so that psi by psi is equal to 1. But even when you do that, still I can change psi by a phase. Because if psi is 1, then this new guy is equal to is still 1. So you still have this freedom of multiplying with phases. In general, you can multiply by any number, but if you insist that I'm gonna use normalized state vectors, even then you can multiply with phases, and that doesn't change even the normalization. So that freedom is still there. Now, let's talk about the next postulate. Which is the time evolution. I'm not really sure, should we even call it a postulate? It is almost a necessity of the sensible, if you want to make the theory sensible. So if you have the state psi, and you have normalized it, you have a normalized state psi, and you want some evolution to happen in the theory. You want things to change. Like if you are describing a system, usually systems undergo changes, and that's the most interesting part of studying something. You have some turn probabilities, and over time they change. Let's say this is at t is equal to 0, at t is equal to t naught. These probabilities have changed. So how can they have changed? One possibility, we will see that we can look at it in many, many different possibilities, but the ones which we will see right now is that first it was given by this. I'm assuming that state vector is, I'm working with the normalized state vector. So later on, my Hermitian operator has same eigenvectors. The Hermitian operator is fixed, so it has whatever the set of eigenvector is there, and I'm finding that getting a particular observation, what is the probability of that? And if the system is changing, those probabilities should change. If they're not changing, nothing about the system is changing. There's no change I can detect. So how can it change? It can change if this psi changes. So before you had psi of 0, now you have psi of t, and psi of t is not equal to psi of 0. So that this scalar product would be different, and you will get different probabilities at a later time. So it makes quite perfect sense. This is your Hilbert space. You're starting from some psi, and the changes in the system you describe by how the state vector of the system changes. So it moves around in the Hilbert space. and you can pick it at any time. And whatever the state vector becomes after some time, you can find all the information is still contained in the state vector. It just keeps changing from time to time. And you can pick up how the information about it, which is all the information is what are the probabilities about the state vector of different observations of the system, how they are changing. So they will change because these numbers will change. Now, the question is how to describe this change. How does it change? Well, the one thing you want is that psi t if it's normalized before, then later on it's still normalized. Because you started with a vector and you could compute the probabilities doing this. Now you use the same formula with this new one. And if it is not normalized, then these probabilities will not sum to 1. So if they sum to 1, then this has to be still equal to 1. And it would be completely nonsensical if the system starts in a state and you compute probabilities through a formula, and after some time system goes into a state where the probabilities, the formula you use for the probabilities does not even sum to 1. That means the probability is leaking away or coming in, which makes no sense. The total probability should still be 1. So what would this imply? This would mean if I write evolution operator. So what is evolution operator? There is some operator which takes my psi from 0 to psi at t. And I want this scalar product to be preserved equal to this same scalar product, which was before. So how will that happen? I can bring it here to a dagger. And this evolution operator, this is giving me the law of evolution, or how the system changes for the system. It tells me that when I start from any vector, how it changes over a certain time. Now this should be true for this. I want to pick one law. So it's like giving a law for the evolution. It's giving the dynamics for the quantum system. It should be true for wherever I start. Wherever I take the system, I'm trying to give you one law, one operator, which tells me how it changes. So U of t, the time evolution operator, operator is the quantum law for describing the changes in system. So what is our assumption? Assumption is an operator exists which describes for us how the system will change with time, starting from any particular, from any state. So this law should be true from no matter where I start from. So that means this should be true for all vector psi. So that means U dagger U is identity. This implies U is a unitary operator. So you can say, call this postulate. Postulate says the time evolution is described by a unitary operator. And this operator has a parameter. U of t has a parameter where t is the amount of time by which you want to evolve. So t, the time, t is the parameter in this operator, and you pick this parameter, you pick a different operator. And that operator tells you how far you are evolving. So clearly it will be like a sequence of operators. As I change t, I'm picking these operators. I'm not drawing a diagram in the Hilbert space, but some space which is containing these operators. As you change t, you are picking the next, continuously picking a sequence of operators. Now from here, you can say that suppose we consider evolution for a very small time, infinitesimal amount of time. So you will be then able to write it. So it's a very small amount of time. So when this epsilon becomes 0, that means I haven't evolved at all. So it should be very close to identity. It should start with identity. And then I have to add something to it. I'm just by convention, which depends on this parameter. When this parameter becomes 0, this extra bit goes away. It's a small parameter. By convention, I'm putting a minus and an iota and a constant. This constant is called, this is all convention. You don't need it, but it has been historically there, so I'm writing it like that. This constant is called the Planck's constant. And then some other operator. Because overall it's an operator, so this is an operator, this is an operator. This is a reasonable form if you are considering very small infinitesimally close evolutions. But I want it to be unitary. So what does this condition imply? This implies U dagger is 1 plus iota epsilon h bar h dagger, and U dagger U so it has 1 plus iota minus iota plus higher order terms, which I'm neglecting to this order. I'm doing only infinitesimally close evolutions. So it will be equal to 1 if h dagger is equal to h. This implies this u that this h which I had put in to write infinitesimally close evolutions, this h is Hermitian. What happened? Okay. So infinitesimally close evolutions are described by a Hermitian operator H, and it is given a name Hamiltonian. So to pick up a law, we will see in a minute that actually finite evolutions can also be described by this H. So to give the evolution law, you have to give this unitary operator, but it's equivalent to giving this Hermitian operator, which is the Hamiltonian. So it's up to you. It's up to the system that what is the evolution which describes it. So depending on what kind of law it has or what kind of law you want to give it, you want to give it in the terms of you are constructing a theory of something and you are trying different laws. So what you are doing is laws of evolution. You're basically picking up different Hamiltonians. But it says that you have to pick a Hermitian operator to do that. Now, we can see its effect on a state vector. So as I said that this should be able to do it on any state vector. So I start with a state vector at time t. This changes it evolves it and changes it to the state vector at time t plus epsilon. But this is 1 minus iota epsilon over h bar h psi of t And over here, I'm gonna Taylor expand it. This is a state vector, but its labels include some real numbers. So I can, it's just a function which takes values in the vector space. But that's okay, I can still Taylor expand it. When I Taylor expand it, I get an expansion in epsilon with evaluated at time t. So what does this give me? They cancel. And I get, well, not like that. When I open it up, I get this term. And this acting on psi of t. Then this term. So these go away and epsilons cancel, and I get H bar what's wrong with this thing? This is called the time-dependent Schrödinger equation. The name is coming because of a huge amount of history. Otherwise, it's a very simple statement. It's just the statement that when you have an evolution, which is unitary, you're describing it through a unitary operator, then infinitesimally, that same statement looks like this. And this statement is just called the time-dependent Schrödinger equation. Now, you can also see that over here, nowhere did I assume that this H itself does not depend on time. But if H is time independent, that means at each time I pick the same H. Because for operators themselves, I can pick a parameter. And at each different times, I'm picking a different operator, like I did for you. But if I pick this kind of evolution where no matter where I start from, whatever u of t is, whatever value I put for t, going from t to t plus epsilon, I always do it using the same h, then I'm picking the same h every time, so h is time independent. In that case, this can be solved through this. Solution for time-dependent Schrodinger equation. It's only a formal solution. Psi of t would be e to the, will there be a minus? We can fix it. What did we put it over there? Yeah, we put a minus. Where this exponential of the operator, you understand it in terms of the series of the exponent. You just have, this is just square, first power, then square, then cube, and so on. So you can explicitly check that this is a solution of this equation, because if I, with the initial condition, so this is psi of 0, that psi starts from this fixed vector psi of 0. Because if I do this, so I get iota h bar into minus iota over h bar h. And since h commute among themselves, doesn't matter, you can write it here. This formula only works if the operators over here, they all commute with themselves. There's only one operator, there's no plus over here. So this just works. Iota minus iota gives you 1, h bar cancel. So this is h, and this is just psi of t. So that means that the time evolution, first we had written the infinitesimal form. But this you can exponentiate. Well, actually, you could have done it this way as well. You apply it n times and then take the limit that n is very large, epsilon is very small, and epsilon n is equal to some finite time. I think we did this kind of a thing in GR as well. With this limit, you will create exactly the exponential, which we have over here argued through other means, that for a finite t, this gets exponentiated. And this is called the time evolution operator. This takes you from psi 0 to psi t. And you can, oh, sorry, there's a t here, not epsilon. And you can show Well, very easily. That if you want to go from t0 to t, then this is just t minus t naught. I'm not going to do it right now. Let's just leave it as an exercise. And you can see it explicitly that it's unitary. Because if I do u dagger of t, it gives me iota t over h bar, h dagger, h is Hermitian, and these two guys are inverses of each other. Because if it's the same operator, that commutes. So in that case only, you can add them. And gives you identity. Now, should I talk about the operator? Okay, let me talk about this postulate. 5. It says that, well, it can be approached to different means. This is called the quantization. The right way to approach it is the following, but I will not do it because to do that, I'll do it at a later stage because we will probably need it for doing more advanced work. But over here, I'll just give you a simplified form, which we can take as the starting point. So the right way is the following. In classical mechanics, since we haven't studied classical mechanics, that's why I'm not doing it over here. You have canonical variable. Q and P. Or you can take any variables. You can take any functions of these variables as well. Then they are called the canonical brackets. Canonical bracket of Q and P. This is called the canonical coordinate. This is canonical momentum. Well, there are usually many of them. And you get something like this for canonical bracket. The quantization rule is that change these coordinates to operators. Let me write with same. My tablet is acting very funny. You change them with operators acting on your Hilbert space. And you don't need to know what this canonical bracket is, but you change it to the operator bracket, which just means this kind of operation on the operators. And that, if you have a 1 here, you replace it by IH bar. And that's it. So it tells you what kind of operators you should associate with the things which appear in classical mechanics, which are coordinates and momenta. You can think of this literally as coordinates in the easiest form, coordinates of particles. And these are the momenta of particles. And in classical mechanics, all other quantities are functions of these. Like you can make certain certain combinations to write momentum, angular momentum and other quantities. They're all functions of these. So then this quantization process tells you in that function, replace the coordinates with these operators. Now, what kind of operators are these? There is a theorem. By the way, this algebra, when you take two operators and put them equal to a constant, the commutator, this is called the Heisenberg algebra. Heisenberg algebra. There's a theorem, we can't prove it here because we won't take this point of view, but it's a theorem which says that this algebra has only infinite dimensional representations. So you cannot represent it only on any finite dimensional Hilbert space. So if you have to deal with these kind of operators, you have to deal with operators for position and momenta, which you want to have this kind of relation among them, then you are forced to work with infinite dimensional Hilbert spaces. So that's the reason I said that no real system in the world has finite dimensions, unless you focus on some specific properties of it. Like if anything is moving in this space, then it has a position. And positions cannot be described on any finite dimensional Hilbert space. You are necessarily required to consider infinite dimensional Hilbert spaces. But instead of going this route, we will write it in a simplified way. We are just writing some postulates. We can write in any form we want. So simplified form. Of postulate 5. Operator for position is represented in an infinite dimensional Hilbert space, and taking it to be L2 the operator x hat can be described by x hat in basis x, so that action of x hat on functions is just xf. So the this position basis we were taking, and we were saying that there's a corresponding operator x hat, which of which these position basis vectors are eigenvectors. That operator is the position operator. And momentum is described by, in the position basis, minus iota h bar d by dx. So it's K, which you were dealing with, multiplied with H bar. H bar is again there just because of historical reasons and because of some units. You can put it equal to 1. So momentum and position operators are the one which we were studying. You can take it to be postulates. And then all other quantities which are functions of position and momentum, you get them just by replacing these coordinates and momenta by the corresponding operators. Now, there are some complications over here. So for example, you can have, if I take this quantity and I ask what is the corresponding quantum operator? Is it this? Or is it this? Or is it this? This is not equal to this because x hat and p hat do not commute. X hat, p hat plus p hat, x hat is equal to iota h bar. So x hat, p hat is equal to minus p hat, x hat plus iota h bar. They're not equal, but classically the quantity doesn't matter. These are just some variables. You write them like this, they're all equal. So if you have a product of x and p appearing in your classical expression, then it's not obvious that how to go to the quantum case. If there are only products of x being added to products of p, then it's fine. But if it's not, then it's not obvious which one to pick. Sometimes there is a hint. Well, in case of one product, there is always a hint, because if I look at this guy, I want to pick Hermitian operators to describe observables. What is this? This is by Hermitian rules, p dot, p dash, p dagger, x dagger. But p and x themselves are Hermitian because they're describing observable quantities. So they have to be Hermitian. And that's why we had taken care to make k and x Hermitian in our Hilbert space. So p dagger is p, this is x, but this is not equal to xp. So that means x hat p hat dagger is not equal to x hat p hat. So x hat p hat is not Hermitian. Similarly, p hat x hat is not Hermitian. Out of all possible choices, only this one is Hermitian. So then you pick only this one. But if you have higher powers, then even this is not enough to pick a particular choice. Then it becomes only a matter of experiment, that which one works better for you. There's another issue which is actually related to one of the previous postulate. So it was for postulate 3. I said, if you are picking the eigenvalue omega I and you want to find this probability, then it's equal to, let's suppose we are taking normalized state vectors is this. But what if omega I is degenerate? Which WI you put in over here? So suppose it's twofold degenerate. just for simplicity of argument, twofold degenerate. What does that mean? What does this word twofold mean? That means you have only two linearly independent vectors. Let's say 1 and wi2, for which you get the same eigenvalue. So which one you put in here? This one or this one? And actually any linear combination of them also has the same eigenvalue. So which one you put in here? Well, that's not how you deal with it. You imagine it in this way. So the best way to think about it is that in the Hilbert space, for each basis vector corresponding to your operator's eigenbasis, you have a basis vector 1, 2, 3. And when you make a measurement, your system is living in some, I don't know what's this doing. My tablet is kind of stuck, needs to be restarted. Your system is living in some vector. The probability that you will find a particular eigenvalue is about its projection onto the corresponding eigenvector. When you're talking about the probability of an eigenvalue which is degenerate, then the correct way to think about it is like if this is Wi1, Wi2, that you will project to one basis vector, but you don't know which one. You can project to this or you can project to that. So the probability is that either you get this or you get that. They both happen to give you same number in terms of the eigenvalue, but they are considered to be distinct. So you either get the Wi from this or from that. And you know very well that when you have an OR statement in probability, then you add them. So you will have this kind of addition. And you can also write it in the following way. You make the projection vector, project it on to the corresponding eigenspace, and then you just compute the probability from there. So what is the projection vector? No, not projection vector, projection operator. So you want to project to this eigenspace. It is a two-dimensional eigenspace. So it would be pick any basis, any orthonormal basis in this, and make this object. Make this object. Now this X, if you act on psi, is going to pick the component of psi along its first. So you are projecting it into your subspace. Doesn't matter which basis you pick up. It just resolves the psi along that basis. So this hits it over here and picks it, the component along W1, 2, and it also hits the other one and picks the component along this one. And it creates the projection of psi on this. So then what this says is that you project along that and then compute the modular square of that. Now, there is another postulate which I should have discussed when I was discussing these probabilities, but I didn't discuss it that time. Let me do it now. No, I'm gonna call it postulate 6. Maybe it's nice that we didn't discuss it at that time. It's called the collapse of the wave function. When you make a measurement or observation, same thing, different words, of an observable with Hermitian operator, let's say omega, and find, now you know that you will find as your outcome one of the eigenvalues, and find, so suppose, so one has to be realized. There is a probability beforehand, you cannot tell which one it will be, but in practice, not in practice, when you will do it, when you do the actual experiment, you will get one particular eigenvalue because your meter will read only one value. And find eigenvalue, let's say Wi. Your system changes its state to Wi immediately after the observation. What does this mean? This means your system was being described by a state psi. Maybe it was evolving like that. At any particular time, it was psi of t, and it was being evolved according to this law, according to this evolution operator, a smooth evolution according to your law. It says that when you make a measurement, then this law breaks down. This law doesn't apply. You make a measurement, you find eigenvalue in your measurement apparatus, you find Wi. It forgets what it was doing. As soon as you make a measurement, it jumps. It jumps from here and lands at the corresponding eigenvector which you have found. It collapses to the eigenvector which you have just measured. And it should be like that, because suppose if it was here, right now you measured Wi, and you just want to confirm that you have measured it. If you measured it again and it was in the same state, then there will be a probability that you won't find it again. So then how in the world you can ever know that you're measuring anything? How can it even be called science if you cannot, like, right away confirm it that this is what you just measured? But this is what it happens. It collapses and it brings out huge troubles in the interpretations, which we will discuss probably later. But one thing to note is that the regular evolution of the system, that's completely gone when you measure. So when you measure, you disturb the system in a huge way. you do not, then it does not care about its own evolution, does not care about anything else. It just jumps to whatever you have measured at this moment. So, any question? Any question? If not, I'll stop here. And how come there's no question? How come everyone is getting everything? Okay, I'm gonna stop here.